Hello guys. Good morning to all of you. Today in this session we'll be discussing a very important topic from classical mechanics, and you can see the title: periodic motion, small oscillation and normal modes. So in every CSIR paper you will get to see one problem from this particular topic, and that is why this is under our top 100 most important topics course. You can get the link of this course in the description, and you can, if you want, you can purchase this course. Before I start, let me know if everything is all right, so that we can start today's session. Before I start, okay. My audio is all clear. Without further ado, let's start. Good morning, Harry. Okay, so what is given in this particular topic? What kind of questions you can expect? So here you will be given some kind of coupled oscillators, and you have to find out like the normal mode and normal mode frequency. So very simple thing, I will just explain to you how you will calculate, then you will understand. So we are taking a spring mass system. The spring mass system is looking like this. So it's a coupled system. So these are, let's say, two rigid support, and we have masses placed in between. Let's say I have a mass here, one mass here, and another mass here. And let's take them of equal mass. This mass is m, this mass is m, and these two masses are connected via a spring like this, and this has a spring constant, let's say k, and this mass is attached to this rigid wall by some other spring, and it has a, let's say, spring constant is 2k, so 2 times of this between this, and here there is another spring, and it has also the spring constant, let's say 2k. You know the spring constant. Now you see, let us say this is the mean position of these masses. This is the mean position of this masses, means about this position the mass will oscillate. So if you, let's say, displace one of the masses, you see the length of these springs will change, and as a result we will have potential energy and kinetic energy as well. So let's say that this, let's say we are considering this to be mass 1 and this is mass 2. Okay, you can imagine it like this is mass 1, and you can imagine it like this is mass 2. So the displacement of mass 1, we are denoting it by x1, and the displacement of mass 2, we are denoting it by x2. Now to find out the normal mode and normal mode frequency, we need to find out a matrix kinetic energy matrix and potential energy matrix. So first of all, so you can give the heading normal mode and normal mode frequency. And let me tell you, this is one of the easiest topic of CSIR-NET, and if any question comes, you can easily answer them. So if I want to write the kinetic energy of this system, what you can write? Kinetic energy is written as T. You know the formula, half m v square. So here two displacement for this mass, the kinetic energy contribution will be x1 dot square. For this one, mass are same, so half m x1 dot square is the contribution from this mass, and from this mass it is half m x2 dot square. Okay. Now what about the potential energy? Look, kinetic energy does not depend upon the length of the spring. It only depend upon this displacement. Okay. Actually, this is a velocity, right? So what is the potential energy? V is equals to, you see, there are three changes in the springs. Three springs, so you will have three terms. Firstly, for this spring is half, or is the formula half kx square. This is the potential energy formula for a spring. So half into 2k. Here the corresponding displacement is x1. It is x1 square plus half k. So this k involves the displacement from both x1 and x2. So this will be half k x2 minus x1 or x1 minus x2. Very right. Plus here, or it is only x2, half times 2k times x2 square. So this is the potential energy term. So if you little bit simplify, what you get, let's say x1, if you take half common, half into 2k x1 square, and from here you will get 1 x1 x square, x1 square. So this will become 3 by 2 half into, then say 3k x1 square plus half into 3k x2 square you will get, minus you will get k into x2 x1 or x1 x2. Now you need to express them in terms of half to get the calculation very easy. So in that logic we have written half into 3k x1 square. We are not writing 3 by 2 k x1 square. Actually the same thing, but this will help you to write the matrix half times 3k times x2 square. Now k into x2 x1, so we can write half minus half into, we can write k times x2 x1 minus half into k times x1 x2. Okay, now we have to form two matrices, T which has component T11, T12, T21, T22, and we have to formulate a potential energy matrix. The elements are V11, V12, V21 and V22. Now how these components are found, that is the question. So T11, how will you find it? You have to take square double derivative v square T11, so x1 dot square del x1 dot square at x1 dot is equals to 0, x2 dot is equals to 0. What does it mean? You will take the derivative with respect to x1 dot square and you will put x1 dot is equals to 0 and x2 dot is equals to 0. This is your T11. What will be your T12? Del square T12, so del x1 del x2, and as usual we have to put x1 dot is equals to 0, x2 dot is equals to, and you can imagine the third term. If I am writing it here, T21, what will you write? Del square T by del x2 dot square, x2 dot, sorry, square not be square, del x1 dot at x1 dot is equals to 0, x2 dot is equals to 0. Now T22, So del square T by, it is appearing 2 times del x2 dot 2, so 2 times square, at x1 dot is equals to 0, x2 dot is equals to 0. In this way you have to find out the 4 elements of this kinetic energy matrix. I hope this is clear. Here Harry, where is Murli today? Now to write this V, what we have to do? Let us try to write V. So here the elements will be something like V11, let's write V11. So this will be, here you see, in case of kinetic energy, it is a function of velocity x1 dot, x2 dot. But potential energy, it is a function of the position coordinates x1, x2. So in finding the component of the velocity matrix, we have to take the derivative with respect to position coordinates. So del square V 1 so del x1, so del x1 square. Here instead of putting x1 dot and x2 dot, here we have to put x1 is equals to 0, x2 is equals to 0. Here only coordinate is involved. V12, you can write it as del square V by del x1, and for 2 it is del x2. We'll put x1 is equals to 0, x2 is equals to 0. T12, there is no dot in the derivative. Oh, sorry. Thank you, Murli. V21 will be del square V by del x2 del x1 by putting x1 is equal to 0, x2 is equal to 0. V22 will be del square V by del x2 whole square. Putting x1 is equals to 0, x2 is equals to 0. Everything is all right. So for the present case, we can write this kinetic energy matrix. So sometimes people give a symbol like this. If you want to give, you can give for the sake of formality, but just an exam. So for the present case, we can write the kinetic energy matrix. So T11, T12, T21, T2. We can simply express it as like this. We have as discussed in the matrix chapter. So this is your T11, 12, T21, and now why did I tell you to write in this way? You see, if you take the derivative with respect to x1 dot square 2 times, you see it will become m x1 dot, then it is m. Okay, there is no x1 dot x2 dot term, so that will be 0. For this one, if you take derivative with respect to x2 dot square, it will give you m. So whenever you write it in terms of half into something into the corresponding position or velocity coordinate, that term in the bracket will be the component. So you can blindly write T11 will be m, T22 will be m, other terms will be 0. You don't even need to calculate, because if you could write in terms of this, like half into this thing, into whether it is for position, it is x1 square means this will give you v11 term, x2 square means this will give you v22 term, x2 x1 means this will give you v21 term, x1 x2 means this will give you v12. And remember, every time plus will be there. So here it is plus, here it is plus, so it is like plus half of minus kx2 into x1. So we can also just modify this little bit to make this formula more straightforward. Okay, let me give you. So we are writing it plus, here you write minus k, here you write minus k. So we can directly write, you see, 3k minus k minus k. V11, V12, V21, V22. So V11 is 3k, V12 is minus k, here it is minus k, here it is 3k. That is why I told you to express it in this way. Whatever terms will be there in the bracket, that will readily go as the matrix component. You can manually calculate by using this. The formula I gave you, you will get this one. Now once you find these matrices V and T, we need to find out normal frequency. What you have to find, what you have to do to find normal mode frequency, we need to do V minus omega square T equals to 0. This you have to remember. V minus omega square T is equals to 0. So we have this matrix V is this 3k minus k, 3k, and omega square T. So this becomes m omega square. So 3k minus m omega square, and this is only minus k. Yeah, this is only minus k. Here 3k minus m omega square. Once again, this is equals to 0. Okay. And if you just simply calculate, so this will become 3k minus m omega square whole square minus k square is equals to 0. You can just use the formula of a square minus b square. So it is let's say 3k minus m omega square plus k into 3k minus m omega square minus this is equals to 0. Therefore, you see, if you take this one, you will get omega is equals to root over 3k plus k by m, and if you take this one 3k minus k by m, so you can write it in this way, 3k plus minus k by m. So this will give you the normal mode frequencies. Omega 1 is equals to root over 2k by m by taking k minus here. If you take plus, what will you get? 4k by m. So this is the normal mode frequency. Now one set of line you write for any value of omega I, one can find the vector, let's say ai, which will satisfy the equation. So it is like the characteristic equation as you have seen in the eigenvalue equation, right? So v minus omega square t, if you just multiply vector, you will get let's say v, so we can write it vij, okay, times ai minus omega square tij times ai. It is just like ai has been multiplied with v minus omega square t, so this will be equals to 0, and this vector ai AI is identified as the normal mode corresponding to the normal mode frequency omega I. So for this present case, we can write it in this way. What we had 3k minus m omega square minus k minus k 3k minus m omega square times ab. This is equals. So you can imagine it in this way. Normal mode frequencies are the eigenvalues, and the corresponding eigenvector is known as the normal mode. Two things: normal mode and normal mode frequency. Normal mode frequency is like eigenvalue. Normal mode is like the eigenvector. Do you have any question, guys? Tell me, Harry, Molly. This is the pretty much theory in this topic. If you understand this much theory, then that is sufficient for us to move forward. Any question? Hello. Let's quickly do this problem. For the system of two identical masses of mass m attached with the ideal spring of spring constants k1 and k2 as shown in the figure, if AB are points are rigid, the normal frequencies are. Do it quickly, guys. You can take the displacements in this way. Take it x1, take it x2, and just follow the procedure. Quickly tell me answer. Could you find the answer? Just follow the previous steps which you have done in the last slide. Here the spring constant, you can see between m1 and m2 we have k2. For this one it has k1, and for this one it has. So what you have to do, we have to first write the kinetic energy term. What is the kinetic energy term? T half m x1 dot square plus x2 dot square. So this is not going to change. What about potential? Half. Here it is k1 x1 square plus half times, here it is k2. So for k2 it is x2 minus x1. Both displacements are involved, and here only x2, half k1 x2 square. Can you write it? So it is half k1 x1 square plus half k2 x2 square minus k2 times x2 x1 plus half k2 times x1 square plus half k1 times x2 square. So you can take x1 square common, half x1 x square common, sorry, half times, you see here k1 x1 square and here also k2 x1 square minus, so plus half times minus 2 k2 x1 x2 plus half times minus 2 k2 x2 x1. अच्छा 2 क्यों होगा? Okay, which option you are getting? Plus half times k1 plus k2 x2 square. So t is equals to, just write it, am 0 0 m. What about v? Is k1 plus k2 minus k2 minus k2 k1 plus k2. So for normal mode frequencies, you have v minus omega square t equals to 0. So k1 plus k2 minus m omega square minus k2 minus k2 k1 plus k2 minus m omega square equals to 0. Follow the steps, previous step. Actually this is the same problem with some value change. Still, if you want to learn, we have to k1 plus k2 plus k2 minus k2. Can you write it? k1 plus 2k2 and it is k1 minus m omega square. So omega, from the first term you are getting root over k1 plus 2k2 by m. Let's name it omega 1 and omega 2 root over k1 by m. So it is matching with option C. Yes, Harry. Okay, let's move on. I hope this is done. This came in December 2013. Consider a particle of mass m attached to two identical springs, each of length L. Very good. And a spring constant K. So length of this spring is L, length of this spring is L, and they have a spring constant K. The equilibrium configuration is the one where the springs are unstretched. So this is their equilibrium condition, unstretched. There are no other external forces on the system if the particle is given a displacement along the x-axis. You can see this is the x-axis and the particle is given a displacement. So the particle has been displaced along this. Which of the following describes the equation of motion for small oscillation? So obviously if you push this block, these springs will be stretched, will be elongated actually, and if you just release this bob, what will happen? If you release this particle, it will execute simple harmonic motion. It will oscillate and it will show a small oscillation. This will become like this. The spring will be elongated. This will also get elongated. So obviously if this length is L, length of the spring is L, here the length of the spring is L, this length will be more than L, right? So let's say this is this angle is, let's say, theta. So for obvious reason this length will be theta. This length is given to you L, this length is given to you L, and if you have displaced it, let's say, by an amount x, let's say this length is x, what will be this length? This length will be root over L square plus x square. And if you sorry, if you see a force will act along these directions, spring force F, so here one coordinate involved x, we can easily find out the kinetic energy of the system. Look, equation of motion we have to find out, so we need to use Lagrange equation. Lagrange's equation of motion. To find out the equation of motion, you have to use Euler-Lagrange equation. To find out the Lagrangian, we need kinetic energy and potential energy term. So kinetic energy is quite easy. Kinetic energy of the system, the kinetic energy E will be given by half m coordinate, so x dot velocity. This is simply the kinetic energy. Now what is the origin of the potential energy? The origin of the potential energy is the displacement. So you make a displacement and as a result the spring is elongated, and that change in length is stored as the potential energy of the system. So what will be the potential energy? Potential energy is given by, if I write it as V, so half kx square. X is the change in length. Okay, this is the main formula, half kx square. K is a spring constant, x is the change in length, and this law is known as Hooke's law, right? So V, here two springs are involved, one is this, another one is this. Natural length is L and the changed length is L square root over L square plus x square. So what is the change in length of the spring? So half k, if I talk about the first spring, change in length is root over L square plus x square. This is the elongated length minus the natural length if I take a square. So this gives you the potential energy originated from the first spring. Now for the spring, down spring, second spring, we have to write it in this way. Half k, spring constants are same, change in length here is also same because the configuration is symmetric. Clear? So it is 2 times of this, so half k root over L square plus x square minus L whole square. Now to simplify this expression, what you need to do, you need to expand it in a Taylor series expansion. Remember, this is small oscillation. Small oscillation means this x is small, x is very small, otherwise it would not be a small oscillation. For small oscillation, for the case of small oscillation, we can use Taylor's expression, Taylor's series expansion to simplify V. So V is equals to look, x is much less than L. X is very small with respect to which x is much less than L. It means x by L is much less than 1. So somehow we need to find out a term which will involve x upon L. Here root over L square plus x square is there. If I take L square common from this root, it will come out as L, and from the square it will come out as L square. So k times L square. Inside the bracket we have taken let's say L square common, so 1 plus x square by L square, and square root was there, so let's give the square root, and we have taken L common from this third bracket also. So L we have taken common, so L square, so it will become minus 1. Clear? Yes, the special function sort was very peaceful. Yeah, group 3 we have already covered. Okay, I will try to make it available. We have already taken that one shot group theory. Okay, for the time being, let's focus on this. This is equals to KL square. Now we can expand this in Taylor series. So if you we have already discussed Taylor series, so there is no issue in understanding that. 1 plus, it is half times x square by L square. Now you see x by L is much less than 1, so not much higher term will survive. So minus 1 by 8 x by x to the power 4 by L to the power 4, and let's say plus so on, minus 1 whole square. Now you see this plus 1 and minus 1 is cancelling, and all the higher order terms are ignored or neglected. So what you are left with? We are left with k L square into, so it is approximately, not exactly equal, approximately 1 by 4 x to the power 4 divided by L to the power 4. All other terms are neglected. X by L is much less than 1, so higher powers of x by L are neglected. In fact, we can write x square by L square. So look, if something is less than 1, its higher power will be even lesser than 1. You see, if I take less than 1 means half. So if you take higher power, square 1 by 4. Okay, if you take cube, it is 1 by 8. So higher power, you can see it is changing drastically. If it is, let's say, 1 by 9, 1 by 9 square, you can see 1 by 8 to 1. So if something is less than 1, their higher powers will be even very much lesser than 1. So let's simplify a little bit. What you are getting, k times x to the power 4 divided by 4 L square. Therefore, we can write the Lagrangian of the system. Lagrangian means the difference of kinetic energy and potential energy. Simple thing. So we have calculated the kinetic energy and potential energy both. Kinetic energy was half mx dot square. Potential energy we have just got k times x to the power 4 divided by 4 L square. So the Lagrange's equation of motion, how can you write the Lagrange's equation of motion? You can find by using the Euler-Lagrange equation, that is d dt of del L by del x dot minus del L by del x equals to 0. d dt of del L by del x dot, it is equals to what happened to my throat, mx dot minus del L by del x. So what you will get here, minus minus plus 3 by 4, acha 4x cube. So 4 getting cancelled, so x cube by L square and k is multiplied, kx cube by L square, this is equals to 0, and that makes it mx double dot plus kx cube upon L square equals to 0. So this is your equation of motion and it is matching with option A. So you see how simple this question is. Let me know if you have any query, confusion from this problem. Okay, let's do this problem. The time period of the simple pendulum under the influence of the acceleration due to gravity g is t. The bob is subjected to an additional acceleration of magnitude √3g in the horizontal direction. Assuming small oscillation, the mean position and the time period of oscillation respectively of the bob will be. Okay, so this is, we have this problem we have kept under the small oscillation, but you see this is a general physics problem. You will see in your NET exam there will be some question which is not categorized in the syllabus. There are some general physics problem will be given to you which requires your a normal like physics concept. It may be, I cannot say out of the syllabus because the NET syllabus is so huge, it can correlate with anything, but there will be some problem which it is very difficult to categorize, like from class 12 level questions. So here what you are given, just try to visualize this thing. You are given the time period of a simple pendulum under the influence of the acceleration due to gravity. You try it by yourself. I'm just trying to explain. We have, let's say, a pendulum like this. At the end of the pendulum there will be a bob like this. So it is making an angle theta, and as this bob is there, it will have tension on the wire along this, and the time period under this configuration, you see, so this bob will be oscillating like this. So there will be acceleration due to gravity which is acting downward every time. And what you can do, let's say this is the extended part. So if this is theta, this angle will automatically be theta, and this is your g. The bob is subjected to an additional acceleration of magnitude √3g in the horizontal direction. Which is the horizontal direction? This is your horizontal direction. So along this horizontal direction, √3g is given. Assuming small oscillations, the mean position and time period of oscillation respectively of the bob. Understood the question, guys? Look, if G acts here and here, and let's say this is the tension T. So if G is this, the effective G will be somewhat along this direction. So that is G prime. So if a vector has two components, one is G, another one is √3g, what you can write? Okay, first of all, T, we know it, 2 pi √L by G. Now after giving this horizontal acceleration, T will not be T, it will be T prime, 2 pi √. Look, L change, length is not changed, okay, only acceleration is given to you, so only G is changing, so G prime. We need to find out this G prime. So now you see this G prime has two components. One is the horizontal component, another one is the vertical component. So it has, let's say, G parallel is equals to √3g, and G perpendicular, it is G. So what is the magnitude of G prime? You know it, √G parallel square plus G perpendicular square. The way you find the magnitude of a vector, same thing here. So this is equals to 3g square plus g square. So 4g square, that means 2g, and hence your T prime is equals to 2 pi √3g L by 2g. So we can write it as 1 by root 2 times 2 pi root over L by g, and this is nothing but t, so t upon root 2. Now we need to find out the mean position as well. Time period we have found out, that is t by root 2. So there is only one option. Even if you do not calculate in the examination, you will get option C. But let's see how the effective mean position of the bob will be 60 degree to the vertical. So it is actually talking about to find the value of theta, right? Now let us try to decompose the component of t. So if this t is this and this angle is theta, we can say this component of t is t cos theta, and another component of t will be the t. Look, if your vector is going along this, your components will be horizontal component and vertical component, right? Now if a vector is coming here, you can write the horizontal component and vertical component in this. It is like that. T is going inward, so the components will be also inward. So we have t cos theta. What is t cos theta? T cos theta is basically the component of tension. Tension is what? Tension is force. Tension is force. So if g is the acceleration and let's say m is the mass of the bob, so mg is acting along this t cos theta. So t cos theta is nothing but m times g. And what about t sin theta? T sin theta is this m times root 3g. Same simple formula, mg formula, m times root 3g. So if I take the ratio, let's say t sin theta by t cos theta, so that will become tan theta. Tan theta is equals to mm getting cancelled, root 3 g by g, so root 3. So for which value of theta? Tan theta is root 3, 60 degree, and that is why this option C is correct. T cos theta outward direction. Oh, sorry, I have given outward direction, na? It should be inward, na? Yes. Is it clear? Now I am going to give you a very important formula, okay? You will remember this formula, and this type of problem if comes in future, you will be easily able to do it. I don't know why so many tractors are coming. Just give me a moment. Okay, just remember this very special formula. Maybe you will be able to solve direct questions from this. If a particle is said to move in a potential like this form V of x, let's say, if you are given a potential like this k x to the power 2 alpha, you have to represent it in this way, k x to the power 2 alpha, then the time period of the particle t will vary with energy in this form. T is proportional to e to the power 1 minus alpha divided by 2 alpha. Okay, E is the energy. So very important formula. Let me show you one problem, came in December 2018. Just utilize this. You have to first represent k x to the power 2 alpha, okay, not alpha, 2 alpha. If it is 6 or if it is, let's say, 8, alpha will be 4. 2 alpha is equals to 8, so alpha is equals to 4. And t will vary as e to the power 1 minus alpha by 2. Okay. So if you have written, just try to solve this problem. The particle moves in the one-dimensional potential V of x is equals to alpha x to the power 6. Okay, sorry, ax to the power 6, where a is greater than 0 is a constant. If the total energy of the particle is E, its time period in a periodic motion is proportional to. Can you do this? Tell me which of the options will be correct. Tell me the answer quickly. Option A? Yes. So this is a short trick actually. Here, if we say 2 alpha equals to 6 means alpha is equals to t. The time period will vary as proportional to e to the power 1 minus alpha divided by 2 alpha e to the power minus 1/3. Option A. So let us try to understand the genuine solution. Okay, you have got the answer from the short trick. In your examination, if you are given a problem like this, you can do it in fraction of in few seconds. Okay, now let's try to understand the actual solution. Actual solution is also very easy, but it will be a little bit lengthy. So what we have to do in this kind of problem, we need to take up the Lagrangian approach. Ax to the power 6, this is given to you, where it is also given a is greater than 0. So for the particle, the Lagrangian will be t minus v. T is Here x coordinates are involved. So what is the kinetic energy? Half m x dot square will be the kinetic energy minus the potential energy is given to you, a x to the power x. Simple. So once you get the Lagrangian, we can write the Lagrange's equation of motion. Lagrange's equation of motion you can write. What will be the Lagrange's equation of motion? D dt of del L del x dot minus del L del x equal to 0. Right? So this will give you mx double dot. Just avoiding few steps, I'm doing it directly. So minus minus plus 6 alpha 6ax cube 6ax cube x to the power 5. Now you know the equation of simple harmonic motion, x double dot plus, you know it, x double dot plus omega square x, na? We know this is the formula for simple harmonic motion. We need to express it in that way. So what will you do? 6a by 5. We can, if we write x to the power 4 times x equals to 0. Okay, we can write it in this way. Now x is a variable. If I write the total kinetic energy, total energy, let's say total energy E naught is the sum of kinetic energy and potential energy. So as you can see, you can say that it is moving in the simple harmonic motion, periodic motion. It is exhibiting periodic motion. So remember this, we have identified it as the simple harmonic motion, and in simple harmonic motion the average kinetic energy and potential energy are same. What happened? ये कहाँ से आ गया भाई? बंद हो गया. In a simple harmonic motion, the average kinetic energy and potential energy are same. So we can write it as 2 times of the average potential energy. You can write. So this is 2 times ax to the power 6. So from here, what you can find out? What is x? X is equals to E naught by 2a to the power 1 by 6. Okay. Look, we don't have problem with this x. It is there in the formula. We have the problem with this x to the power 4, where we cannot keep x here. So that is why we, from the known condition, we are finding out the value of x. And as a result, we can write, let's say name this equation 1, equation 2. Therefore, equation 1 becomes x double dot plus x to the power 4, this is 6a by m. X to the power 4 is E naught by 2a. To the power 4 means 4 by 6 means 2 by 3. Can you write it? And that x thing will remain as it is. This is equals to 0. Now comparing this equation, okay, let's move simplify a little bit more. X double dot plus 6a by m into 1 by 2a to the power 2/3 e naught to the power 2/3 times x equals to. So compare with the simple harmonic motion. Compare with the equation of simple harmonic motion x double dot plus omega square x equals to 0. So what you will get? You will get omega square 6a by m 1 by 2a to the power 2 by 3 e naught or 2 by 3. So omega is equals to root over 6a by m and is 1 upon 2a to the power 1 by 3 and e naught to the power 1 by 3. Can you write it? Omega is nothing but 2 pi by t. So t is equals to 2 pi root over m by 6a 2a to the power 1 by 3 e naught to the power minus 1 by 3. Can you write it? And that is why we can say t is proportional to all these things are constant. E naught to the power minus 1. This E naught is the energy. So you are getting E naught to the power minus 1 by as usual. If you are getting allergy with E naught, let's write it as E. It will finally match. Is the total energy. Tell me if you have any question. Let me know when it is done. Hurry up, guys. No strength है. Short trick saves a lot, right? You see how much things. But why did I tell you this complete procedure? You need to know the actual solution as well. Short trick is good. That will give you instant relief. But if you learn the solution, this exact solution, if you learn, that will help you to visualize the overall thing correctly. And if you combine both short tricks and the actual solution techniques, you get the complete knowledge. That is essential. Many times short trick doesn't work. Okay? Here the concept comes into play. Okay. Do this problem. The time period of a particle of mass m undergoing a small oscillation around x equals to 0 in the potential v equals to v naught cos hyperbolic x by L is. Can you do this? Actually, this problem is from the previous chapter. No? So here it is not in that form of x to the power something. Here it is given cos hyperbolic. So we know the formula of time period 2 pi root over t is equals to 2 pi by omega, na? 2 pi omega is equals to root over k by m. So 2 pi root over m by k. And what is this k? K, we have already done this calculation, detailed calculation. K is given by del square v by del x square at the stable equilibrium position, like x equals to x0. Here it is given already x equals to 0, so it is x equals to 0. Can you do this? Just take the double derivative. Cos hyperbolic x is equals to e to the power x e to the power minus x divided by 2. Sin hyperbolic x, this. But the fun fact is, derivative of cos hyperbolic x is sin hyperbolic x, and derivative of sin hyperbolic x is again cos hyperbolic x. Tell me the answer quickly. Okay, let's move forward. Cannot wait all day. Look, v is equals to v naught cos hyperbolic x upon L. And as you can see, if you take the derivative of cos hyperbolic, it will give you sin hyperbolic. And if you take the derivative of sin hyperbolic, it will give you the cos hyperbolic back. Okay. So it is undergoing a small oscillation around x equals to 0, meaning around the stable equilibrium point. So for equilibrium point, what you have to do? For equilibrium point, we need to take the derivative with respect to x and equate it to 0. So here already it has mentioned you about x equals to 0. Okay. So we can take x equals to 0 as well. Del v by del x, it is equals to so v naught upon L. Derivative of cos hyperbolic is sin hyperbolic. Let's say if I am putting x equals to x0, now what you need to find out, we need to find out k. K is equals to del square v by del x square at x equals to x0. Here it is 0. Okay. So we have taken derivative with respect to x once time, so this will be v naught upon L whole square. Sin derivative of sin is cos hyperbolic x naught by L. There will be no negative sign. Okay, it is hyperbolic, and in hyperbolic, if you take the derivative of sin hyperbolic, say e to the plus x, it is the plus e to the power minus x by 2. So it is giving only plus cos hyperbolic x. There will be no minus sign. You can do it. We have to put x naught is equals to 0. Okay. or you can simply write it in this way. So cos hyperbolic 0 is to 1 plus 1 by 2, so 1. So that is why it is V naught by L. So omega root over k by m. So root over k by m is this V naught by L whole square. So what you will get? Have I done any mistake? Root over k by m. So this is V naught by m L square. Acha, we have done a little mistake here. V naught by L. There is no square in V naught. V naught by L square. Okay, let's keep it like 2 pi by omega 2 pi ml square by V naught. Which option is it matching with? C. Is it done, guys? Tell me quickly. This x naught is creating extra problem. Is it done? Can we move forward? Okay, one last problem from this particular topic. This came in June 2019. Read this question out. Two particles of masses m1 and m2 are connected by a massless thread of length L. So you see m1 and m2, and this is some platform, a hole is there, and through this hole you can see a thread. This thread has a total length of L, and it is connecting the two masses m1 and m2. So as you can see, if you just keep it in this way, you do nothing, what will happen? This mass will be stuck here. But if you take this mass and if you rotate, the centrifugal force will take it outward, and because of that this mass will be maintained here. Okay na? So this is what it is talking about. Two particles of masses m1 and m2 are connected by a massless thread of length L. So this mass, you can take the mass of this thread is 0. The particle of mass m1 on the plane undergoes a circular motion of radius r0. Can you imagine? An angular momentum L. When a small radial displacement epsilon, which is much less than r0, means you just displace it a little bit. So what will happen? Its radial coordinate is found to oscillate about R0. Okay. The frequency of this oscillation, you can imagine, if you just displace it little bit, what will happen? It will be like this kind of motion it will exhibit. You have to find out the frequency of that oscillation. Understood the question? A little bit difficult question, but lengthy question, not so much difficult if you just follow the steps. Let us try to do this problem. First of all, you will try to write the equation of motion for these two masses. So one thing is clear, if you see, first of all, we'll take up the case where the particle is moving in a circular trajectory of radius r0. Then after that, we'll give this small radial displacement later. So when it is moving in a circular track of radius r0, what is the equation of motion for m1 and m2? Look, gravitational acceleration due to gravity is acting downward. So first of all, let us try to write the equations of motion for the masses. The question is simple. You see, you can imagine a table. A table is there, and in the middle of the table there is a hole, and two masses are connected by some massless thread of length L, and one mass is on the table, another mass will be under the table. Now if this mass moves in a circular way, so you have just taken the mass, okay, and the mass is moving in a circular trajectory in this way. What will happen? This, because of the circular motion, this mass m1 will feel an outward force, centrifugal force, right? Outward centrifugal force, and that will help to keep this m2 steady at this point. Okay. Now what it had said, that a small radial displacement means along this, if you took the mass and just give a radial displacement, so what will happen? It will oscillate about this mean radius or not, will like this in this way. So you have to find out the frequency of that oscillation. Okay. After giving the radial displacement, it will execute oscillation. So what will be the frequency of that oscillation? Well, let's solve this problem, then you will understand eventually. Equations of motion. Firstly, we will be writing for m1. For m1, what will be the equation of motion? You see, here we will be using Newton's second law. As per Newton's second law, force is equals to mass time acceleration. So here acceleration is what? If you consider r to be the radial coordinate, acceleration will be r double dot. Okay. So m1 r double dot. This is the effective force acting on the mass m1. Now as you can see, when this is moving in a circular trajectory, if the centrifugal force acts along this, the tension in this thread T will be acting in the opposite direction, right? T will be acting along the opposite direction, and this centrifugal force which is taking it away from the center, and when the balance is maintained, this will move in a circular trajectory, right? So what is the centrifugal force formula? M r square, m r theta square, right? Theta dot square. Actually m omega square r, na? Theta dot is equals to omega. M omega square r is, this is the centrifugal force. So you see, T is acting along opposite direction. So m1 theta dot square r centrifugal force minus tension. Look, if this tension would have been greater, then this mass could not sustain the oscillation, could not sustain the circular path. Right? It would have come down to this. So m1 theta dot square r minus t. So that force is m1 r double dot. So what is this force m1 r double dot? m1 r double dot means it is effectively acting radially outward, right? Radially outward in this way. Now if I talk about the second mass for m2, what will be the equation of motion? Now if you look at this here, in which direction tension will work? You see m2 is pulling it down, so obviously the tension will act in the opposite direction, and along this direction the gravity is pulling it down. Now once again, if this m1 is overcoming and it is effectively going outward, you see which one is greater force here? Obviously the tension in the string will be greater, and that is why it will be maintained in this position, otherwise it would have come down. So for m2 it is T minus m2g. So this is the effective force acting upward, right? It is acting upward, right? And this is equals to m2 r double dot. Now you imagine acceleration would be same for both the masses. They are connected by spring. So here you can keep a note. Acceleration would be same for both the masses. So these are the two equations of motions. Now it has angular momentum L. Mass m1 has angular momentum L. So what you can write? It is a kind of central force motion, right? So angular momentum will remain constant. Angular momentum L is given for mass m1. L will be, what is the formula of angular momentum? mr square theta dot. m1 r square theta dot. This is your force. Let's name this equation, equation 1, equation 2, and this is equation. Have you understood this one? This is the main thing of the calculation. Later on, whatever calculation you will be doing, that it will be just the follow-up. This is the main thing. Do you understand this equation of motions and the angular momentum? Tension value is same, only the directions are changed. So putting the value of T from equation 2 into equation 1, we get. Harry, tell me if any question you have. Murli, is everything all right? So you see m1 r double dot is equals to m omega square, so theta dot square r minus t is equals to m2g plus m2 r double dot. Okay. Now let's take this r double dot common, so m1 and plus m2 r double dot minus m1 theta dot square r plus m2 g equals to 0. That is m1 plus m2 r double dot minus m1 r theta dot square. We can put the value from here. Theta dot is equals to L by m1 r square, right? From it we can find out the value of theta dot. Theta dot is equals to L by m1 r square. So we have just put the value of theta dot square plus m2 g is equals to, because theta dot equals to L by m1 r square. Clear? So this is, let's say, 4. One thing, do you understand what is r here? R is the distance from the center. Okay, r is the distance from the center. So as you go along this, your r is changing. Now when it is moving in a circular path, what is the change in r? Change in r is r dot, right? R dot is 0. What is r double dot? R double dot is 0. If it is maintaining a constant radius, what will be r double dot? R double dot will be 0 there, because there is no change in r. So when it is undergoing a circular motion, you can see it is undergoing a circular motion with radius r naught. So we can put r double dot is equals to 0. For the circular motion of m1, r double dot is equals to 0. If we put r double dot equals to 0, therefore we can write from equation 4, we get, put r double dot is equals to 0. So what you are left with? L square divided by m1 r cube, the minus sign. This will be equals to minus m2g, and from here you get the value of L square, that is m1 m2 times r naught cube g. So for circular motion of m1, r dot double dot equals to 0 and r is equals to r naught, right? Here I is putting r equals to r naught. Let's name it equation number. Now we are in a position to take care of the small radial displacement. If you, let's say, from r equals to r naught, if you change the radial displacement, small radial displacement epsilon, if you apply, so it will oscillate. It will not be able to move in the circular path. It will oscillate about the stable radius r naught. Now a small oscillation or a small radial displacement epsilon, where epsilon is much less than r naught, has been provided, has been applied. So look, previously if it was moving, let's say, in a radius of r naught, previously it was moving in a radius of r naught. If you give a radial displacement of epsilon, let's say, it can go up to this radius. This is r naught, and this is your R naught plus epsilon. So now what is the radial displacement? R. R is equals to R naught was previously, now you give displacement epsilon. Epsilon much less than R naught. And now you just put this value into equation, into this equation number 4. R double dot, what will be R double dot? So if R is equals to R naught, your R dot is equals to epsilon dot. Look, R naught is constant, epsilon is not. So R double dot will be epsilon double dot. R naught is a constant, remember, but epsilon is not a constant. So if you put this thing into equation number 4, what you will get? M1 plus M2 R dot. So this calculation this was for when R is equals to, this is a general, actually this is general for any radial distance R. Now here we have used for a particular radial distance R naught. Now for R is equals to R naught plus epsilon, how the equation of motion is changing, that is what is happening. Oscillation is happening along which direction? Okay, this along the outward direction. No, it is like let's say something is moving. You imagine that thing. Can you imagine the configuration? Two masses, one is above the table, another one is pulling it down underneath the table. Now the mass on the above, it is making a circular motion in this way. So obviously they will try to push the mass away. So you will just take the mass and just try to push it in this way away. Small displacement, radial displacement you give. So what will happen? Look at this. If you give a small displacement to this mass, so obviously this whole string is connected, right? So if you put a radial displacement along this direction, this mass will be little bit up. Okay. Now because of making balance, what will happen? This mass, gravity will work on this mass M2 and it will come down again. So when it is going here, this M2 mass will be up. Now because of this M2 mass, it will come down, and you see previously it was there, so it will eventually come here. Okay. Now again it will be like this, like this, like this, like this. You try to imagine, because this string is fixed. So if you just give a displacement, this M2 mass will try to make a balance and it will oscillate about this stable radius. If it is a small radial displacement, then it will oscillate in this way, you can see. Understood now? So R will be equals to R naught plus epsilon along this direction, outward. That is why we have written R plus epsilon, R naught plus epsilon. Even if you write R naught minus epsilon, the result will be same, because when you calculate epsilon dot, it will be same epsilon double dot. But it is taken outward, not inward. Inward, then it may disturb the oscillation, because as it is moving about R naught, you must give it outward, not inward, because this mass has a tendency to go inward, right? Because of the M2 mass, it pulling it down, this M1 mass has a tendency to go inward. If you give an inward displacement, it can all come down, so that will not sustain. So that is why this radial displacement must have been given in an outward direction. So just put the value minus. Okay, now what is left? M1 R L square by M1 R cube. Okay, L square by M1 R cube. R is equals to R naught plus epsilon. Just put the value of R naught plus epsilon. This is equals to minus M2G. Okay, na plus M2G. So okay, let's keep it plus M2G. This is equals to 0. Now little bit of calculation. Let's tackle this R naught plus epsilon cube term first. So when it will go in the numerator, it will become R naught plus epsilon to the power minus 3. Now we can expand. Look, epsilon is much less than R naught, so we can make use of the series expansion. If we take R naught common, so it will come out as R naught to the power minus 3, 1 plus epsilon by R naught to the power minus 3. Now since epsilon is much less than R naught, what we can do, we can just expand it in series. R naught minus 3, and we are just 1 minus 3 epsilon by R. This is equals to minus M2G. Okay, now we can just put the value of L square. Now we have got the value of L square here, M1 M2 R naught cube G. M1 M2 R naught cube G. So R naught to the power minus 1. Equation 5. Okay, let's do a little bit of simplification. M1 plus M2 epsilon double dot minus let's R naught cube getting cancelled, 1 M1 getting cancelled. So what you are left with, 1 minus 3 epsilon by R naught times M2G equals to minus M2. And you see M2G is cancelling from both sides. You are left with M1 plus M2 epsilon double dot minus plus 3. But if you think that this problem is difficult, I will just avoid. So you will be in the average, because that is what the average students think. You have to be a little bit more than average to stand out of the crowd. Okay, so take challenges and make a habit of solving difficult questions. So the more you solve difficult questions, the easy questions will appear to be very much easy. Medium level questions will appear to be easy. So this type of question is like the mental exercise. You will not solve in the examination in the very beginning. You will keep these problems to solve at the end. But you should practice and know how to solve this kind of problem.